is one of our graduates. Very proud of him. He also got an MBA at University of Chicago, and he is a big entrepreneur. So we'll hear about what his entrepreneurship involves. So we look very much forward to your talk today, and thank you very much for agreeing to talk to us.
My pleasure, and thanks for having me. I really love an opportunity to get back and talk to some of the grad students at U of I. I'm gonna jump into things here, and I'm a little worried about time because I threw a lot of slides in here, so I might speed talk just a little bit, but I want to make sure that I get a bunch of different ideas across. Really, what I'm going to talk about here is kind of my journey trying to spin a technology out of a university. And I'll give you guys a little bit of my background, kind of where we are today, and try to be as transparent as possible about all of the mistakes that we made, because we made a lot of mistakes. We have been pretty successful too. We have something along the lines of $15+ million worth of investment that's coming into our company. A lot of that is non-dilutive, which means that we're not beholden to a lot of private investors, private capital markets, and some of the baggage that they bring along with them. But I'm also going to talk a little bit about the technical side too, some of the challenges that we saw, and sort of what we're seeing in the industry in terms of a recognition that hard technologies, hardware technologies, deep tech technologies are a very important piece of the overall technology landscape. That there are some ways to get capital into those technologies in the earlier days, but that the bar is still very, very high for what you have to be able to do with your technology once you're trying to cross that gap and get into the private capital markets. So with that, I'll just jump into some quick backgrounds here. So I'm the CEO of SwitchSource. I've got a co-founder, Lane Nelson. Lane is my sort of back office finance guru. So he manages all of our contracting, manages HR, manages IT, manages everything that kind of makes the company run. Whereas I'm doing a lot more of the work on the sales engineering, product development side, and investor management. In addition to the two of us, we've got a couple of people with a little bit more gray hair. Joe Lamoureux, our chief operating officer. Joe came through our network. He was somebody who was kind of in semi-retirement a couple of times. He manages all of our supply chain and contract manufacturing. And then we have Nick Benavides, who's at PCK. But Nick kind of acts as our CTO. So he's the one that is our one throat to choke when it comes to performance and product development. When you are working on newer technologies, you need really, really smart people. Nick is one of our really, really smart people, and he helps make sure that we are able to build the product to the expectations of some of our customers. But the other thing that's great about working with contract engineers as an entrepreneur is that it's something where you can turn off the spigot. So you can hire them to do a specific scope of work. They can complete that scope of work. You can wait a couple of months, see how your clients react to that scope of work, and then go back, make changes, and iterate. And you can do this all while having like a lot of management over your cash flow. Quick background on kind of where the technology came from. And let me take just a step back, give you a little bit of my CV here. So when I came out of University of Illinois, I had participated in a couple of the solar decathlons. I had some exposure to renewable energy. I had a lot of exposure to power electronics. I worked under Pat Chapman. Spent a little bit of time working at Solar Bridge, which at the time was Smart Spark, and then transitioned out and immediately went to work for a large independent power producer, a company called Invenergy. And one of the exciting things about Invenergy was, it was a company that had about 100, 150 people there. They were managing something on the order of 5,000 megawatts of generation, which is a decent, medium-sized utilities worth of generation. Pretty significant amount of wind, pretty significant amount of natural gas-based generation, and they wanted to get into energy storage. That was an area that I owned for the company for a period of a couple of years. We developed the largest fleet of energy storage projects in North America at the time. This was mostly short duration energy storage for doing things like dynamic regulation for the PJM market. And that was kind of my claim to fame, was developing a lot of this energy storage. So when I had that expertise under my belt, started participating in these incubators and accelerators, these organizations that are meant to try to seed technologies with entrepreneurs and put a little bit of power behind them, a little bit of capital into them to see what they can do. That's when I was introduced to the technology that was at Michigan State. So this was a technology that was developed under ARPA-E through their GENIE program, which was a Green Energy Networks maybe initiative. And the idea here was the Obama administration was seeing a lot of large scale renewables, so big wind projects, big solar projects getting killed because of interconnection costs. So the idea is the grid in that area where there was a lot of renewable energy resources didn't have load. And so these projects were getting saddled with huge transmission costs just to interconnect to the grid and get the power where they wanted it. So the Obama administration started throwing money at ways to more intelligently route power out on the transmission grid as a way to decrease those interconnection costs, increase sort of the renewable energy receptivity of the transmission grid. Our professor built a beautiful prototype to demonstrate his novel power flow control technology. He called it a transformerless unified power flow controller. It's more of a CMMI architecture. It's just cascaded modules using some low voltage commodity components to build up to the voltage and power levels that utilities actually care about. And what we found when we initially stumbled on this technology was, hey, this really had the potential to be something at transmission levels. There were already a couple of players at transmission levels with legacy fax devices. But what we found is that the sort of investment versus market opportunity size when we were trying to understand this technology didn't really pencil well for venture capital at transmission levels. And let me kind of unpack that just a little bit. The fax projects that we were seeing that were getting the green light in the US were few and far between. Maybe one or two bids on projects by major utilities every year. And we knew this because we just showed up at the major electrical conferences and went and talked to the major manufacturers of these devices. We went and talked to GE, Siemens, ABB, asked them how much business they were doing, and they were pretty blunt, pretty open about it. It wasn't considered a secret. So we were able to get really good market information about what did the industry actually care about these sort of high voltage power flow control technologies at the time. At that same time, we started getting a little bit smarter about what was happening at the distribution level of the grid. And personally, I'd been spending a lot of time trying to sell energy storage directly to utilities, and found that distribution was an area that they were very interested. But there was still kind of a question of how are we going to make energy storage pencil? The big concern here was around cost, and then if people got around the cost question, a lot of times there were concerns of regulatory issues. Typically utilities have been split into sort of the wire side of the business, transmission and distribution, as well as generation. And here's this asset that looks like it's more of an energy asset trying to play in a wires business. So depending on the state that you're in, the utility might not have the clout to just go to the regulator and say, no, this is a wires asset, we're going to rate base it, meaning getting the customers to actually foot the bill for this. So there's a lot of difficult market dynamics there, and we understood that. This is kind of all of these ideas were pulling together in my head as we were looking at these technologies, and we saw that power flow control could be an interesting piece of the puzzle down at the distribution level. So from there, we've actually developed two different power flow control devices. We have the Phase EQ, which is really focused on balancing power from phase to phase across three-phase systems. Really focused on 4-wire systems is where that device excels due to the topology. And then the tie controller, which is a power flow control device for connecting between two different distribution circuits. I don't want to read this slide to you. I'm happy to share some information, some specs on our device. One of the things that was important to us is that we understood that there were a lot of high expectations from utilities in terms of equipment before they would put it out on their system. And we wanted to make a device that took what was built at Michigan State, which is probably a little bit difficult to see here, but it's this sort of racked system in the bottom corner, and turn it into something that looked more like what the utilities were used to purchasing, more like a no-see green box. And so we had to try and find some partners to help us out. And that'll be kind of a recurring thing as we go through this presentation, is finding great partners to be able to spin these technologies out finding ways that are low cost to those partners, but high value to a startup. And this might be something as simple as guidance when it comes to the standards that you're going to have to adhere to, or walking you through, your specification. And a lot of these major manufacturers will help you do that, help you develop the technology, if you're willing to kind of show them a little bit of what's underneath the hood. Have to be a little bit careful though. So in terms of where we fit into the grid, this was the common topology that we kept seeing. So again, for those that might not be familiar, we're just trying to represent a distribution substation here, stepping down from a transmission or sub-transmission level voltage. So, depending on the utility, 34.5 up to, 138, probably not a lot of 230 going straight to distribution. We've got our medium voltage bus, a number of distribution circuits, and these distribution circuits, feed anywhere from 500 to a few thousand customers. We're talking about 5 megawatts to 10 megawatts of load. Typical distribution voltages are in between 4 and 27 kV, and about 90% of, maybe it's closer to 85% of distribution voltages are a 15 kV class or under. So we had a pretty good feel for what this market looked like, but the thing that was most interesting to us was this normally open point. And this is kind of a key, a key moment that we had as a company where we're like, hey, we finally found where we could bolt on our device, and where utilities are already thinking about how they can exchange capacity from one distribution circuit to the other distribution circuit. So utilities have switches along these distribution circuits. And so when they want to actually balance load out, in this scenario, if they have too much load on this circuit, they're basically going to close this switch and open one that's upstream of it, so that you have less load being fed from this circuit and more load being fed from down here. Similarly, if there's a power outage, something goes wrong, a tree falls on a line here, what they're going to do is they're going to open a switch to isolate that, and then they're going to use this normally open point to try to restore service to the customers that are down on the second half of this feeder. Now, that first use case where the utilities are looking to balance load, that's something that might happen every year to 3 years. And then when we're talking about restoring service in the event of an outage, where you have a tree fall on a line or a car runs into a pole, that's something that might happen, let's call it, tens of hours out of the year. So this was the moment where we had this realization that this is a key feature of the grid, and it is underutilized with respect to how utilities think about their operations. And so we started going out and kind of pitching this concept of putting a tie controller at these distribution circuit ties as a way to give utilities dynamic control over where the capacity was on their system. If the device fails, the system would fail normal, so to speak, and you would just go back to having a normally open tie between these distribution circuits. So again, we really thought that we knocked it out of the park in terms of finding this initial use case, but this is something that's been under development, I would say, for 2 or 3 years now. And one of the things that I'd like to impress the importance of is, all utilities are operating very, we'll say, largely similar systems, but at the same time, they're all unique. They're all little snowflakes. And the only way that you get to understand where those similarities are, in my mind at least, is by going out and talking to a lot of them. And this is something that's kind of a more of a business concept, but this is the sort of data that's difficult to capture when you're doing like a survey of utilities. Like if you're doing a survey of utilities, you can get a sense of how many circuits that they have. You can get a sense of very aggregate data sets of what's the total number of megawatt hours that they're selling. But there's going to be a lot of unique things about the operation of that utility that are due to what the climate is like, where that utility operates, what the regulatory climate is like. So are they encouraging solar, or are they blocking solar when it comes to addition of distributed generation at the distribution level? There's all of these dynamics, and you can get a good feel for that by reading the 500-page integrated resource plan for a distribution utility. But it's a hell of a lot easier to pick up the phone and call them. And I know that that's not something that us engineers are always comfortable with, but it certainly is going to potentially save you some time. So just to throw that out there, we learned a lot about all the problems that the utilities were facing by going through the I-Core type programs that are hosted by NSF, where there's an emphasis on customer discovery. And that's how we were able to kind of find a place for this pre-baked technology to fit out on the grid. Now, one of the ways that we really tried to focus on selling this technology was a comparison to energy storage. We saw this as if you have a control point between distribution circuits, we like to explain it as you're using the capacity of one distribution circuit, using your tie controller as the energy storage inverter, and then giving commands to either charge the battery by pulling power away from the circuit or discharge the battery. The reason that this is important is because, believe it or not, power flow control is a tougher concept for people to grasp as opposed to energy storage. Everybody has energy storage, they've got a battery in their pocket. When you're trying to talk about the benefits of power flow control, as opposed to just manipulating switches, you have to get a little bit clever with kind of explaining these technical concepts. And I won't say that we've perfected it, but it is something that you need to be able to speak to kind of all levels of an organization. It can't just be to those distribution planners, distribution engineers, protection engineers. It has to work on multiple levels. The last thing that I think is kind of goes back to this idea of talking to distribution utilities is kind of one of the key places where we see a lot of interest in our device. So our technology can act a little bit like, we'll call it a solid state transformer. That doesn't really tell you a lot of what it's doing, but we have the ability to swallow phase shifts and then also voltage magnitude jumps. And when you're a utility and you have a system like this, you might be thinking, well, why in the heck would they have two distribution circuits right next to one another and then not design them for the same operating voltage? That's a pretty good question. A lot of this has to do with how utilities have developed over the years and the fact that they've been purchasing a lot of smaller utilities. So there's been consolidation in terms of the utilities that are out there. And what happens is the people that are making those consolidation decisions don't necessarily get out into the weeds at the distribution level and understand compatibility of systems. And even if they did, I'm not sure that they would really care because it's just limiting how you can perform with regards to reliability. It's also going to be triggering more frequent upgrades because you can't just switch to balance load between these two distribution circuits. You're going to probably have to whole cloth rebuild one of these distribution circuits, which could be a $3 or $4 million investment easily. So this is an area where having a drop-in solution that can allow utilities to better dispatch load across normally open ties that they can't close has been a very interesting area. Because of the scale of the utility industry, in the utility industry, there's about 200,000 distribution circuits that are operated just domestic in the US. We still see that there's large number opportunities. We're talking hundreds, if not more than 1,000 opportunities, very similar to this, where we see sort of incompatible voltages across a switch. So these are the sort of strange, nuanced problems that you'll find in the distribution world, only if you corner distribution planners, distribution engineers, distribution operation folks, and kind of talk to them. Because a lot of times with these problems, they've been living with it for so long, they don't even think of it as a solvable problem to discuss. It's just like an operational limitation. And those same people aren't necessarily going to be thinking or be savvy about the capabilities of new technologies to resolve some of those problems. So that's kind of all I had on the application side. I'm happy to stop for just a minute if there's any burning questions, but I can also, we can wait to the end.
Is your market primarily North American, or are you selling in other parts of the world as well?
Right now we're targeted on North America. The reasons for that are really just kind of ease of access. We do find one of our devices, the Phase EQ, works better on 4-wire systems, and we see a lot of Delta overseas. A lot more 4-wire here in the US.
Hey, Charlie, this is Pete Sauer.
Hey, Pete, how you doing?
Hey, great to see you. How does that tie controller fit with what S&C Electric might produce? Do they have an equivalent?
So S&C Electric would focus more on automating the switches that are along this path, and then they would have a software layer that they'd put on top of that to coordinate those switches, and they'd call that like Flizzer. I'm not going to take a stab at the acronym there. Pete, is that what you had in mind, or
Yeah, is that a competitor for you or what?
It's a little bit of a competitor, but even the most sophisticated utilities are still doing a lot of that Flizzer open loop because they're concerned, do I have enough capacity to bring this chunk of load from one distribution circuit to another distribution circuit? The key benefit for us in those systems, you have to look at it more on a network level. But if you have 3 distribution circuits, you really want to be able to have a solid state control of how much power is going from distribution circuit to circuit. You can get a pretty good sense of power by number of customers and then split it up by the number of switches. But we think we kind of cut right to the heart of it when you're talking about controlling power flow.
Yeah, because that's the big issue with tap changing under load transformers. You have to put them both on neutral before you close the switch.
Yes. And so a lot of them will not do closed transitions. And so you end up with, the saying is drop and picks. You drop customers and then you have to pick them back up.
Yeah, good idea. Congratulations.
Thanks, Pete. So let me talk just a little bit about the MVP here. And I've got a lot of slides, but I'm going to fly through them. So, I think that it's worthwhile taking a look at this article. This was something that Rocky Mountain Institute put out there. And typically there's this sort of like valley of death idea with startups and technology companies. And what Rocky Mountain Institute said is like, hey, look, it's even harder for a lot of energy related technologies. There's actually something more like 4 valleys of death. There's kind of proving the basic concept, maybe spinning it out of that research area and trying to put, more of a sort of like outside academia team on it that's just solely focused on it. Then there's, getting to a real minimum viable product, proving that minimum viable product, and then making sure that you get, market validation. With what we're trying to do, it's really tricky developing hardware. The time cycles are really long, and there's been a lot of great technologies that have struggled because investors in the VC community want things to move at a certain pace. And when they don't move at a certain pace, there tends to be the solution of, well, we'll just throw more money at it. And that's actually a lot of times the opposite of what needs to happen. You need more time and maybe not as much money. You need to be a little bit more lean. That's something that, I feel like we've done a pretty good job of in terms of taking money only when we need it. Again, we've been really fortunate with the non-dilutive capital. The reason that a lot of that non-dilutive capital, and that's code for grants, the reason that we've been successful with a lot of that is because there's a lot of institutions like the Department of Energy through ARPA-E, NYSERDA in New York State, CEC in California, that are interested in these technologies, and there's just a dearth of companies that are chasing them. And the reason is because it's really, really freaking hard. And if you're willing to do something that's really, really freaking hard, the point is there are these organizations out there that want to help you. So it's not always easy to find to do that matchmaking, but it does exist. And a big reason that it exists is because of an emphasis on clean energy technologies and getting more of them out on the distribution grid. At least, for my sort of myopic view of focused on wires infrastructure, that's how we've seen it. So, this is what everybody would probably like me to talk through is giving the details of how our technology works. I wouldn't dare do that, with this audience. I will just say that the sort of core trade-off that we're making with our technology, and there might be a few, is this idea that if you can take commodity off-the-shelf components and put them into a cascaded architecture, where you have a building block that's maybe rated for 1200 or 1700 volts, and then you stack those building blocks up so that you can reach higher voltage levels in some sort of partially rated converter design, then you might be able to come up with power flow control technologies that are at a lower price point than doing sort of like a transformation down to a 480 volt level, doing a back-to-back conversion, AC/DC AC, and then stepping it back up with another transformer. So there's some sort of elegance there, but what you're trading off is that you are going to have to deal with a lot of different modules. You're gonna have to deal with a lot of communications to those modules. And then you're gonna have to deal with a bunch of problems around creating a utility grade version of this device that has all of the sort of isolation that you need for creepage and clearance distances, but also for the BIL ratings that your device is gonna require. So there's a lot of baggage that is just table stakes to get a piece of equipment in the ground with a distribution utility that, to be blunt, is not necessarily thought of when you're doing the basic research stage. What you're trying to do with the basic research stage is to prove out that sort of the magic of this works, that you can get some power flow control, and then what you have to layer on top of that is the next 15 slides here, which we'll jump through kind of quickly. Which for us we called the sort of unknown challenges. The known challenges, this is stuff where you don't want to reinvent the wheel. So again, if you're looking to innovate a new technology, and the example that I'll give was there was somebody that I was sort of mentoring that was trying to come up with a technology that was able to sort of turn energy associated with a dance floor into energy that could get injected into the power system. And they were spending all of their time really focused on the power electronics interface. And it seemed to me that, like, if you could take anything off the shelf to shorten your product development cycle so that you could be more focused on what makes your device special, that's something that you want to do. And that's part of this idea of the minimum viable product. It's, you don't have to own everything end to end. You're not Tesla right now. You just need to get something that's able to roll down the street. So, for us, we took, thermal management system designs, the HMI for SCADA, everything in terms of the power interface, being able to isolate our device, the circuit breakers, and we just took it from people that were willing to work with us at the time. Again, asked from them things that were low cost to them, but high value to us, which a lot of times is just getting a few hours of their time and contribution throughout the project. Now, the unknown challenges, I'm going to try to go through these because I think some of these are kind of fun, but I want to give a sense of how complex this device is. So we build our power electronics into these modules. Each module is 2 H bridges, and this is what a single phase diagram looks like for us. So there's 7 modules on the shunt. We split it up just in terms of the connections to make it a little easier to have 4 modules on one series branch, 3 modules on the other. When you total all this up, you've got 42 modules per device, 84 H bridges that you're controlling. I'm sure everybody here has kind of some sense of fundamental frequency switching, how you could come up with a sine wave from this sort of cascaded architecture. You can layer a bunch of clever things on top of this in terms of selective harmonic elimination, and doing some things where, again, you're trying to mix in some optimization. Are those MVP type things? Maybe not necessarily. You also want to make sure that your device doesn't get rejected based on power quality. Now, one of the continuing issues that we have here, just as sort of a motif, is this idea of how do you then explain this, these concepts to somebody who really hasn't seen power electronics before at all. And those, for the most part, are the power systems engineers that you're going to be interacting with, the experts on what they actually need to have control over out on the distribution grid. And there's a certain level of comfortability that they need to achieve. They don't want to just think about a black box or sort of a magic box connecting to their system. So there's different ways to try to explain what we're doing underneath the hood, whether it be with controllable voltage sources, or having them think about them as controllable impedances to be able to control power flow from one distribution circuit to the other distribution circuit. These are the sort of things that take a decent amount of time to develop. And I will say, some of the best engineers we have are the best at coming up with these analogies to help explain them to the distribution utilities, to the people that are actually doing the technical due diligence. Let me skip that. So I wanted to show a little bit about the process, kind of running a little tight on time here. So let me just fly through this. We worked with a top tier manufacturer for our power electronics builds. So what you have here is cold plate, IGBTs, gate driver boards on top of them. You have a local voltage supply board, communications board that's stacked on top of this. These are our capacitors. So because we're more of a per phase device, as opposed to, you know, a 3-phase device with a common DC bus where you're expecting things to be very balanced. There's a decent amount of ripple, and your capacitors get pretty damn big. And then, you know, when a utility opens this up, they want to make sure that the system is dead. You know, utility, one of the number one concerns, there's several number one concerns of a utility is safety. And they want to make sure that you don't have so much stored energy inside your device that somebody's going to get zapped. So, you know, these are resistor bleeder boards that are sitting on top of them. These are all of the pallets of our power modules that go into a single unit. And granted, this is a pretty beefy unit. This is a 10 MVA unit. You know, and to compare that, again, we're not an energy source, but if you look at, you know, I like to look at sort of like gas or diesel engines to get a sense of like what those power ratings and power densities look like compared to our device. And I mean, if you got, you know, 2 MVA worth of generation on like a 20-foot shipping container, I think you'd be doing pretty good for yourself. So going 5-fold that with power electronics is not bad, not too bad at all. The rest of this is really trying to wrap all of these, you know, sort of interesting power electronics in very, very boring enclosures to get the utilities as comfortable with it as possible. I won't go into any more details here, but you know, this was a very fun and exciting process. And it was so fun that it actually distracted us from a lot of the things that we needed to focus on. When we pulled everything together, were we able to modulate the system and create the voltages we wanted? Yes, everybody was very happy and we were high-fiving around that. But there were a lot of these sort of, you know, oh shit moments throughout this product development. You know, it wasn't all high-fiving and creating these, you know, fairly pretty pieces of equipment. You know, one of the things that we really struggled with is fault handling and understanding that, you know, when you're out on the distribution grid voltages, power quality, how much abuse you're going to potentially have to take from, you know, lightning, where surge arresters are going to kick in. If you're just exposing your system directly with power electronics, to even have, you know, sort of a shot in the dark of really surviving for a long period of time with all the faults that you're going to see out on the grid, you have to be able to control your device fairly quickly. So 500 kilohertz was something that, you know, we worked up in terms of how much potential voltage drop you could see across the power electronics in what period of time if there was a fault. And our power electronics are not rated for sort of like a line to line voltage. They're really rated for kind of a peak to neutral. So like a line to neutral voltage. So the reason that this is all important is because this set the speed at which we had to do a large number of the operations of our of controls of the actual power electronics themselves. So if you're talking to many things very, very quickly, this should have been a red flag to us, you know, right out of the gate, that this was going to be a pretty big lift for us, that the control systems were going to be pretty tough to deal with. You know, this isn't, you know, sort of like aircraft control system speeds necessarily. There are, you know, if you're designing rocket control systems and things like that, yes, they might be going faster than this, but this is pretty brutal, you know, and unforgiving. Then there were some really dumb basic things that we just completely missed. And this is, you know, part of the complication of understanding, you know, what it takes to get out of the lab and into the field. And 100% my fault for not understanding this. But even the pre-charge sequence for us of getting all of our power electronics charged up, awake, so that we could speak to them to be able to understand if there's, you know, faults, reset them, make sure that they have a decent DC link voltage. This is something that took, you know, months, half a year to figure out. So like the smallest pieces here and things that seem really mundane, you know, might not be super attractive R&D challenges, but especially when you're trying to think about taking that step out of, you know, proving that core concept, there might be some really difficult product development challenges that you're still going to have to break through. And honestly, it might not be the most attractive stuff that you spend your time on. You know, pre-charge is not necessarily something that I think we all, you know, get excited about. The last piece of the puzzle here, you know, we took the first look at this topology from Michigan State, and it was in a pretty specific setup. So what we're looking at here, this is these are like PQ charts. So if you're thinking about like a 4-quadrant inverter that could do, you know, real and reactive power. Let's say it was for like an energy storage system, so you have real power going both ways. you would want to see sort of like a perfect square. And what we found is that there were a lot of discontinuities here, in large part because you know, when you think about this device, you should really be thinking about it as being in a three-dimensional space where you have power through the device as one variable, a reactive power on one set of terminals, and a reactive power on the other set of terminals. So you have a Q1, a Q2, and a P. And to understand how this behaves with different system impedances, with different voltage drops, with different phase angle differences, these were all things that we had to kind of canvas utilities to understand what the actual sort of grid conditions would be that we would have to see. And then we had to go back and decide how we were going to be able to manage this with the design of the device. And this led to one of our largest changes, which was going from something which was a shunt series configuration to a T configuration where we have series, shunt, series. So pretty damn big change. And this also changed the controls for most of the device. So we were starting from a blank sheet of paper. When we were all said and done, these are kind of the major control systems and give you a sense of the sort of time constants that we're trying to solve these different things for. This was incredibly difficult. We spent so much time developing the controls for this device, and we're still actively wrapping this up, making sure that you have the ability to jump from point to point, to make sure that all of your DC link regulation across all the modules is still behaving appropriately, that you're getting the right output from your dispatch control and from your current regulators. So there's just a lot of control theory that I would say is difficult to get your arms around the complexity of it, especially when you're trying to model 84H bridges, which is there's shortcuts around that so that you can do better modeling of the controls implementation. But from the get-go, understanding that level of complexity that you have in your system is something that's going to be critical. And it seems silly to us, now looking back, that we thought, hey, we're just going to be able to take this device kind of off the shelf and apply it to, to the grid. And the reality is that, within sort of standard operating procedures for utilities, for the voltages that they could have on these distribution circuits, there would be an incredibly limited set of operating points that we could even hit. So kind of understanding those design requirements and understanding the complexity that comes with it, especially as you're thinking about moving that technology out of the lab and into the field, incredibly critical. Sort of the one piece that I just wanted to highlight in terms of how we screwed up is, it really comes back to this controls development side of things. It's a lot easier to see progress, when you're developing hardware, and it can be more exciting, it can be more rewarding when you're working on that. A lot of the controls got started later because we were so focused on the hardware side of things, and because that progress moved fairly quickly. So we ended up doing a lot of tasks serially, and I would just say, especially when you're trying to show overall progress to a grant agency or things like that, it's important to always be thinking about how you can parallelize these tasks in product development. If I had one wish, it's that I could basically go back and kind of restart the clock, reorganize how we tackled some of this product development. I think that's it. So I will cut it there. I know we're kind of late, but would love to give you guys a chance to ask any sort of questions, really about anything.
Hey, Charles, that's really very, very helpful. And I hope the students were paying close attention, because I can hear all the experiences in many of these startup companies. And of course, as you've learned again the hard way, hardware development in the power industry is a very, very long road. But it sounds like you've managed to get a certain amount of acceleration. Where are, you just talked about some of the things that maybe didn't go quite so well. What were maybe some of the things that went more quickly than you thought, or have you been able to move along as much as you'd really like?
There's things that I would say on the product development that went more quickly were really just a function of us finding the right people. And I think that that's something that's incredibly tough to do, which is probably good for all the students. You're in incredibly high demand, and all of the fields, all of the disciplines that we worked with, I mean, we fought tooth and nail to get the time of the people that were supporting us in those areas. And then, when you get the right people working on the project, it goes a lot faster than you would expect. The one other thing that I would just say there is, we spent a lot of time building relationships with these different utility groups throughout the country. And it takes a lot of time, and you're doing some sort of like remedial work where, they're trying, these organizations might be trying to help startups, and, they want to work with new technologies that have an impact on their business. And if you can go and do those programs, kind of put your ego aside, let them teach you some things, then your success kind of becomes their success, right? Like they feel like they have a stake in your success, and they will help you move along. And that was one of the key things here is, if you're willing to kind of put your ego aside and say, hey, I don't need to take another course on how, distribution systems work, or, talk to a distribution planner and have them handhold for 10 weeks here. If you can put that aside, that really does help speed things up.
Thanks.
Okay, so there's a question here. Can you share some tips on ensuring the reliability of your product, especially when there are many capacitors? So there's a couple of things there. One is making sure that we're regulating the temperature correctly. So you can see, we put a cold plate on the IGBTs so that we can pull the heat right off of the heat source. We also just overbuild the hell out of the air conditioning system for the rest of the capacitors. And then you also overbuild the capacitors themselves, just kind of put in more capacitance than you need. The device that we showed has something like $85,000 worth of capacitors in there. I will tell you, I wish that there was some sort of like elegant solution or something that we were doing that was smarter than everybody else. But a lot of this comes down to brute force. The one good thing about our industry is the utilities want to hear that. They want to hear that you spent more money making sure that this thing is going to live for 20 years. The alternative where you're kind of undercutting something, or you're coming out with like the lowest cost version of this. No, they want to hear redundancy. They're okay paying for it because they don't want to pay it in OpEx, and they don't want to have a failure. Mm-hmm.
Hi, Charlie. Thanks for the great presentation. I'm a little curious about what are the control objectives that your device can follow. I mean, are utilities mostly trying to minimize energy costs, losses?
Yeah, absolutely. So we really fall into kind of three categories of use cases. One is around something that we would call like upgrade deferrals. Now it's been rebranded as like non-wires alternatives. It's a concept of basically, if you have parts of your system that are being overloaded, can you use this device as a tool so that you don't have that thermal overload? It's usually on a substation or a distribution circuit. And so in those cases, a lot of times you're just getting real power set points to be able to balance power during key parts of the day to other infrastructure. This is something that couldn't necessarily be done with just a simple switching procedure. Or again, it might be this issue where you have different voltages around a particular substation, and so you can't shed load to those circuits. The other piece of the puzzle here is, or I should say, the second use case that we see a lot is around solar generation. And so with solar, as you all may have seen, you typically hit, let's first say there's three real limits that utilities care about. There's their voltage limits, and for single phase, they're concerned about balance. So basically, high to low voltage balance across the three phases. But then there's also the sort of ANSI requirements around a plus or minus 5% voltage that they have to give to their customers from a power quality perspective. That's usually the first threshold that you hit. But then beyond that, you are going to hit limitations in terms of the conductors and their thermal carrying, like the current carrying capability of those conductors. And then the last piece is backfeeding the substation, which most utilities see as a huge, tremendous cost. Can be $1 million or $2 million if you're going to generate enough electricity that's going to be coming back into the substation, because they have to upgrade a lot of their protection schemes to know what to do with backfeed. So in those cases, we're doing a little bit of balancing of real power flow from distribution circuit to distribution circuit. And then we put an AVR, an automatic voltage regulator, on the side of the device that's closest to the solar facility to help regulate the voltage. A lot of times, solar facilities these days might have some requirements to maintain current carrying capacity so that they can regulate their own voltage, use the reactive power output. But that's the sort of use case that we want to focus on there with the solar. And then the third piece is the reliability, where again, we wouldn't necessarily be picking up load directly with our device, so being grid forming on one side of our device. But what we're trying to do is, if there's load that had to be switched onto one of our distribution circuits and now it's overloaded, we want to be able to balance that out so that that distribution circuit is kind of being relieved a little bit by an adjacent circuit. So it's a lot of balancing power, and I would love to tell you that it's like a lot of optimization, and that we're doing real like power flow, optimal power flow. It's not. It tends to be a lot of very basic sort of like algebra type stuff.
Thanks a lot.
Mm-hmm.
Do you think you could come up with a high-powered switch that we could use to help out Texas?
I'm not sure if there's any one piece of equipment that's going to help out Texas, but yeah, those things, they certainly help us. Everybody thinks of us when something like Texas happens. I'm not sure if we're the magic bullet solution though, more just a piece of the puzzle.
Very clever, Charlie. Thanks for coming and talking to us.
Appreciate it, Pete. Good to see you.
Yep.
All right, anybody else? All right, well, I did include my email here. If you do have other questions or people just want to, kind of shoot the breeze, if you guys are looking for kind of industry support, we've been pretty successful and got a decent network. Happy to kind of offer it up where we can. So, give me a shout, and I'm happy to hop on a call with you all and help out where I can.
Hey Charlie, there was a question in the chat.
Oh, all right. Well, I think I got this one. The capacitors. Is there another one?
I'm sorry, I must have missed it, but no problem.
All right, everybody. Well, I'm gonna call it there then. Again, don't hesitate to reach out. Happy to help. Wherever I can.